Start karibi. Ah, Now we'll come to the next characteristics of the antenna, physical characteristics that we define, or the next parameter, antenna parameter, not the characteristics. Next antenna parameter is called the radiation efficiency. Now, all these parameters that I am discussing, or that I am saying now, or defining, these will be useful when we'll come to the practical antennas like the dipole antenna or the linear antenna or the microstrip antenna. We'll find out what is the radiation efficiency, what is the directivity, what is the input impedance. Those things we'll find out for those antennas. That is why we are defining these antenna parameters. So the next parameter is the radiation efficiency. The used power value is the only difference between gain and directivity. So how much power is used? Uh, that is the difference between the gain and the directivity. Now directivity gives you the gain. An antenna would have if all input power appeared as radiated power. That is called to P in is equal to P. So P in is the input power. Input power means power input to the antenna, and if that is called to P radiated power, power radiated by the antenna. Suppose you give 10 watt as input to the antenna, and the antenna radiates 10 watt in all directions or in its preferred direction, but it and power coming out of the antenna is 10 watts. Then, and that is what is gain. And this gain, gain is an antenna would have, if all the input power appeared as the output power, that is what is directivity. Directivity is the gain. So directivity and gain are same provided the input power is equal to radiated power. In that case, directivity and gain will be same. Now, gain shows the real antennas and nearby structures consume some of the input powers. That is what is shown by the gain, because gain is less than the uh, total radiated power. So that shows that the antenna consumes some amount of power, the input power, and nearby objects, they also nearby structures to the antenna, they also consume some of the input power. So accordingly, the radiated power is determined from the radiation efficiency. Because gain is less, so radiation efficiency gives you the total radiated power. The radiation efficiency ER, this is the ratio of the radiated power or the desired power to the net power accepted by the antenna. So that is what is radiation efficiency. So radiated power by net power accepted by the antenna. So ER is equal to P by P in. Now P in is the power accepted by the antenna. P in the numerator is the power radiated by the antenna. Now P in you can write as P plus P0, where P0 is the ohmic losses. Ohmic losses means losses are due to resistive elements or resistive values in the antenna, because mostly antenna is made up of conducting materials, so there will be ohmic losses in the antenna. There will be resistance, there will be resistive losses. So losses in the antenna, except for the power loss, the losses in the antenna are P0 ohmic losses. Therefore, P in, total power accepted by the antenna, is equal to power radiated by the antenna plus the power lost in the antenna. So P in is equal to P plus P0. So ER is equal to P by P plus P0. So since ER is equal to P by P0, unless P0 is equal to 0, ER will be less than 1. And when P is equal to 0, radiated power is equal to 0, ER will be 0. Therefore, the limit of ER is between 0 to 1. So 0 is less than equal to ER, or efficiency, radiation efficiency is less than equal to 1. Now let us define directivity in terms of radiation efficiency. D we know is equal to UM by U average. So intensity, maximum intensity by average intensity, that will be maximum intensity by average intensity is power radiated by 4 pi, that is maximum intensity by power radiated. Now you know it is power input, so P in into ER, that is P. So since P is equal to P in into ER, so you can write for P in into ER the by 4 pi. Now UM by P in by 4 pi, that is a G gain is equal to G is equal to UM by P in by 4 pi. Therefore, this will become G by ER. So that implies that gain is equal to D into ER. Since D is equal to G by ER, so G is equal to D into ER. So if a small question is asked you, 2-mark question or 4-mark question for this, you have to prove this. Now, look at this radiation efficiency. We'll look at a more detailed view of radiation efficiency. We have an antenna. Antenna portion is the yellow portion. That portion is the antenna. That is connected to a feeding line. It can be a transmission line, which is the white portion. Now, from the transmission line, power is fed to the antenna. Now, when power is fed to the antenna at the input point, because of the mismatch means because of the characteristics and impedance of the feeding line is not exactly equal to the input impedance of the antenna. So therefore, there will be some reflection. So first point is that at the input point, there will be reflection due to impedance mismatch, characteristics impedance of the transmission line and the input impedance of the antenna are not same. So therefore, there will be reflection loss due to mismatch. So there will be some reflection. So and the power that we are giving, so input power is less than the total power that is given to the antenna. So power input to the antenna is less than the total power. Because there is some reflection, some power gets reflected. Then the antenna is conductor in nature. Therefore, on the conductor, there will be ohmic losses due to the conductor. Because there is a conductor, when power is given to the conductor, there will be ohmic losses and they will be dissipated as heat. So ohmic losses in the conductor. So that is the second type of loss in the antenna, in the structure. Then there will be ohmic losses in the dielectric used in the antenna, because you know no dielectric is perfect. All dielectric will have some amount of conductivity. Because of the conductivity, there will be ohmic losses in the dielectric. So there will be three losses. One is reflection loss, one is ohmic loss due to conductor, other is ohmic loss due to dielectric. So these three losses are inherent in most of the antennas. So E0, we define E0 is equal to E gamma into E sigma into E epsilon. E sigma into E epsilon, and that forms the radiation. Then you will find out what is radiation efficiency. It is E sigma into E epsilon. So E0 is equal to E gamma, E sigma, E epsilon. That is the total radiation efficiency. Reflection efficiency ER and radiation efficiency ER. These are defined as ER for radiation efficiency is equal to E sigma, E epsilon. Reflection efficiency is defined as E sigma, which is 1 minus gamma square, gamma being the reflection loss. So this is how you define the radiation efficiency. Okay. Then we'll come to the beam efficiency. This you have to note down the definition. Look at the beam, the main beam. Look at the main beam. So it goes from minus theta towards theta. minus theta to plus theta in the z direction, and over phi is equal to 0 to 2 pi over the whole of phi. So that is what is in the red, shows it is varying over the phi, and the black lines they show from left side theta to right side theta that we are considering. So beam efficiency BE is equal to total power in the main beam by total radiated power. So total radiated power and total power in the main beam are two different things. Total radiated power is the power that comes off of the antenna and is radiated in the main beam, in the side lobe, in the back lobe, in the minor beam. So all those things they form the total radiated power, and total power in the main beam is the power contained only in the main beam. So BE is equal to total power in the main beam by total radiated power. So that you can write as 0 to 2 pi, that is the variation of phi. So 0 to 2 pi, then 0 to theta, that is the variation in theta for the main beam. So that will be 0 to theta, u theta phi, u is the intensity, so intensity theta phi, then beam will be sine theta d theta d phi. Okay, so over a solid angle sine theta d phi, that you will write. Then undivided by total radiated power is 0 to 2 pi is for phi, 0 to pi is for theta, all angles of theta is 0 to pi or minus pi by 2 to pi by 2, that is all angles of theta, and u theta phi sine theta d phi. So this is how you define a beam efficiency. Then we'll come to the polarization in antenna, when the power radiated by the antenna uh, will contain the electric field and the magnetic field. You know, the orientation of the electric field with respect to the direction of propagation gives you the polarization of the field. When you say the field is polarized, that means how the electric field is oriented with respect to the uh, direction of propagation. Now, when we have considered that with respect to direction of propagation, what we do is we find out the locus described by the tip of the electric field over one period. So when you find that locus, if that locus is a straight line, then we call it a linear propagation. If that locus is a circle, and then we call it a circular propagation, polarization. If that locus is an ellipse, then we call it an elliptical polarization. Now here we are showing a linear polarized wave, a circular right-hand circularly polarized wave, and a right-hand elliptically polarized wave. So when we call it a right hand, if it is propagating along the z direction and it is clockwise direction, rotation is clockwise direction with respect to z direction. When z is away from you, then if it is clockwise, then we call it the right hand circular polarization. If it is anti-clockwise, then we call it left hand circular polarized, provided z direction is away from us. So this is how you define polarization. Now, because of polarization, there can be losses. We'll consider those losses later. Now let us have a closer look at polarization. We have a microstrip antenna. Here you can see there is a microstrip antenna, and the field propagating away from the microstrip antenna is linearly polarized. Electric field is the blue portion, magnetic field is the red portion. So there electric field is in the z direction, so vertical. So it is a linearly polarized antenna. Then we can see another example. It is a circular microstrip antenna. It is, there are two feeds. You can see there are 2 points on which we are feeding the antenna. Simultaneously, we feed the antenna through 2 points. That gives rise to circular polarization. So from a microstrip antenna, microstrip antenna, we are getting circular polarization. Of course, we can use a square microstrip antenna to get a circular polarization. Those things will be discussed later. But this is how we get polarization or the wave coming out of the antenna, if it looks like this, then we call it a linear polarized wave or a circular polarized wave. Now let us come to the polarization losses. Losses due to polarization. Now look at the incident power. So the power incident gives you the field is in vertical direction. So this shows you the field in which the maximum power is there. So it is in the vertical direction. So let us start with that. Then, then this P on the right hand side gives you the polarization due to the antenna, which is slant, which is not vertical. So it is slant. The antenna power, incident power is vertical, that is coming towards the antenna. Antenna polarization is slant. It is not vertical, it is slant, which means since it is electric field, so we will have two components. One component will be vertical, one component will be horizontal. So we'll have PRX, P loss. Why we call it P loss? Because PRX is oriented to P incident. So receive RX is received power. TX is transmitted power. So power received power. So if PRX is equal to P antenna, which means antenna is oriented along P incident, then on the power that is coming towards the antenna will be intercepted by the antenna completely. But if it is antenna is slant, it is not oriented along the power incident onto the antenna, then there will be a problem because it will not intercepting all the power that is coming towards the antenna. A portion of the power will be intercepted by the antenna. Therefore, it will receive less amount of power. Although incident power is P incident, antenna will receive only PRX. PRX will be less than P incident by a value P loss. So the other amount is P loss, that is lost. This loss is called the polarization loss. And we define the polarization loss by PLF, polarization loss factor. That is what is called the polarization loss. PLF is the polarization loss factor, which is equal to P incident, the vector P incident, dot the vector P antenna. So polarization due to incident polarization, dot product with antenna polarization, and that square is polarization loss factor. So that will be, since P incident and P antenna, they can be oriented along the same direction or orthogonally. If they are oriented orthogonally, P incident dot P antenna will be 0. If they are oriented along the same direction, then P incident dot P antenna will be 1. So PLF will be between 0 and 1. So 0 is less than equal to PLF is less than equal to 1. If you express it in dB, then PLF dB will be at 20 log 10 P incident P incident dot P antenna square. So this square will not be there on the right hand side. This square will not be there. So now that on that limit will be minus infinity less than equal to PLF dB less than equal to 0. So that will be the limit in the dB in dB, because 0 if you take its dB, that will be minus infinity. 1 if you take its dB, that will be 0. So PLF in dB will be between minus infinity to 0. PLF in absolute value will be between 0 and 1. This is about polarization losses. And then we'll come to something called freeze transmission formula. Once we come to freeze transmission formula, then hopefully we'll stop for today and we'll look for the quiz examination today. Now, the freeze transmission formula is like this. Suppose you have two antennas which are separated by a distance r. So in free space, we have one antenna, we have another antenna, these two antennas are there. They may or may not be oriented along the same line. So the axis of antenna 1 may not be aligned with the axis of the antenna 2. So these two antenna may have different axis. So the orientation of axis may be different, may be same, but in general they are different. But the difference between the antenna, there is a separation in the between the antenna which is R. Then under that condition, what will be the ratio of the received power to the uh, transmitted power? One antenna is transmitting, other antenna is receiving. Two antennas are there, a transmitting antenna and a receiving antenna. One antenna is transmitting, one antenna is receiving. Then what will be the ratio of the power received by power transmitted? So that will be the when you come to the uh, transmitting antenna, there will be a mismatch loss because of impedance. So that will be 1 minus gamma r square. That will be the mismatch loss due to the impedance mismatch for the radiating antenna or then for the receiving antenna, there will be impedance mismatch loss, which is RTX. TX is the mismatch loss due to the transmitting antenna. RX is the mismatch loss due to the receiving antenna. So there will be two mismatch losses, 1 minus gamma r square into 1 minus gamma t square. So these are the mismatch losses due to the antennas. Then as the electric field propagates in the free space, uh, there will be some loss in the free space, that is called propagation loss factor. As you know, the field varies as 1 by r. So on this loss will be lambda by 4 pi r square. So this is called the propagation loss factor. Lambda by 4 pi r square, capital R is the separation between the two antennas. That is what is called the propagation loss factor. So we'll have some loss due to propagation in the free space. And then because of mismatch in polarization, there will be polarization loss. So that is PLF, polarization loss factor. That gives you the PLF. Then each antenna, each one, the transmitting antenna and the receiving antenna, inherently will have some gain. They will not radiate all the power they receive. There will be some gain because there will be some losses due to ohmic losses will be there or dielectric losses will be there in the antenna. So each antenna will have some gain. So for the transmitting antenna, the gain is GT. For the receiving antenna, the gain is GR. So GT into GR. Therefore, the ratio is PR by PT, that is equal to 1 minus gamma R square into 1 minus gamma T square, where gamma R and gamma T are reflection coefficients. Uh, uh, so the reflection coefficients of the receiving and transmitting antennas. Then lambda by 4 pi R square whole square into PLF into GT into GR. So this formula is called the freeze transmission formula. So if there is a transmission from one antenna and there is a receiving by the another antenna, the transmitted power is received by another antenna. Then the power received by the other antenna can be found out using freeze transmission formula. So this is what is freeze transmission formula. So with this, we come to the end of today's discussion on the antenna parameters. So we complete the antenna parameters. I'll give you some problems to work out. Then there will be a quiz. We'll have a quiz on what we discussed today. Okay. नहीं ये को छाड़ दियो ये को छाड़ दियो Okay. Next. Ah, ah. So this is a take home problem. So you will calculate using the far field boundary criterion of RFF is equal to 2d square by lambda for a linear antenna of length d, and the RFF for the following antenna lengths will be how much? D is equal to 5 lambda, a half wave dipole which is D is equal to lambda by 2, and a short dipole D is equal to 0.01 lambda. And so find out, they solve this problem using the note down the problem and solve this problem. एक काम करो, लिटिल कर दे, सेटू बंद कर दो यूट्यूब। ये था लिटिल के कह दियो।